Well, good morning. My name is Luis Rodriguez. I'll be chairing this morning's session. Thank you very much for being here in time. And our first speaker is Scott Ransom of the National Radio Astronomy Observatory in Charlottesville, and he will be talking about extraordinary physics with millisecond pulsars. Scott, please.
Great. Well, thank you very much. It's a pleasure to be here. Thanks for the invitation to come here. It's been a really nice meeting so far, and I'm looking forward to the rest of the day. So what I want to tell you about today is something a little bit different than what we've heard about from a lot of the other talks. There will be a bunch of gravity, there will be some gravitational waves, there will be black holes. But mostly I'll be talking about the way that we use pulsars as our tools to get at that physics, the physics including the black holes and including the gravitational waves. So I'll give you a little bit of an introduction to what pulsars are, how we use them. I'll explain what pulsar timing is, which is the crucial aspect of how we get this physics out of these systems. And then I'll show you some of the applications, especially gravitational wave detection, which is, you can see the symbol there, nanograv. That's the project that I'm part of in the United States. And actually it's all of North America, the North American Nanohertz Observatory for Gravitational Waves. So I'll explain all about that, and then talk about some of the other types of physics, such as measuring neutron star masses and how that affects high-density nuclear physics, tests of general relativity that are quite unique to pulsars. And so hopefully you'll get a flavor of the type of science that we can do with these amazing systems. So what are millisecond pulsars? So first off, they're neutron stars. So all pulsars are neutron stars. They're the densest, most compact stars that we know of that have a surface. We've heard about black holes all week. They have an event horizon, we believe. But these guys are only a couple times bigger, at least if you talk about stellar mass systems. The radii of these systems are only 2 to 3 times the Schwarzschild radius of a black hole that's about the same size, maybe 3 to 4 times the radius. But they have a surface. They're held up by neutron degeneracy pressure, effectively, and very exotic physics go on the interiors of these neutron stars. At the central densities, at the very centers of these stars, the central densities are many times nuclear density, 4, 5, maybe even up to 9 or 10 times nuclear density. We do not understand the physics that goes on the inside of these neutron stars. They're extraordinary objects even from the outside, though, where we can see them. The cartoon picture on the right is what we kind of generically think of as a pulsar, where there's a dipole magnetic field embedded into the crust of the neutron star, and that axis of that dipole magnetic field does not have to be aligned. As a matter of fact, we think it's probably mostly not aligned with the rotation axis of the star. So that when you rotate that star rapidly, you have a moving magnetic field that induces an electric field, at least in portions of the magnetosphere, and you accelerate charged particles to highly relativistic energies, and that by some still magical means, we do not understand the emission process, we get emission. And a lot of times, most of these pulsars are measured in the radio, and that's why we use the largest radio telescopes in the world. But there's also X-rays and gamma rays, and sometimes, a very small amount of time, optical and infrared light that come out of these objects. Their masses are between basically about 1.4 to 2 solar masses, so incredibly dense objects, especially when you consider they're the size of a city. And then when you also think that they're rotating incredibly rapidly, the fastest known millisecond pulsar rotates 716 times per second. That's faster than a kitchen blender rotates, that's faster than a race car engine rotates, and yet these things are still the size of a city and weigh more than everything that's in our solar system added together. We measure them, though, by these pulsations of light, because this moving magnetic field has irradiation beams that come out of the poles. And so just like a lighthouse, if we happen to be in the path of the radiation, we see a pulsation every time the neutron star rotates. And we can measure these things incredibly precisely. All of the energy that we see coming from these objects is coming from their spin. There's no fusion, there's nothing else. These are spin-powered objects. So they're giant flywheels in space. And yet they can give out a tremendous amount of power. The most energetic pulsars can give off thousands to even tens of thousands of times the total luminosity of the sun. And that's coming purely from rotation. So hopefully from this slide you've seen that these are quite exotic objects. Most of the rest of the talk, though, I will think about them purely as clocks, because the pulsations that we see from these incredibly stable rotating systems come at very precise clock-like ticks, and we can measure those ticks and use them as an instrument to make a bunch of physics type experiments. So let me say a little bit more about how millisecond pulsars are made, because millisecond pulsars are a subset of neutron stars and pulsars in general. So pulsars are formed in a supernova, so a very massive star blows up in a supernova explosion, produces a pulsar, such as the Crab pulsar, which is one of the most studied objects in the sky. That object will last about 10 to 100 million years. That's how much spin-powered energy there is before it slows down too much. And then it'll just be a dead neutron star zipping around in the galaxy. But if there's a companion star, such as our own sun, that's in an orbit around that massive star when it blows up, that star will evolve on stellar evolutionary timescales, which is probably billions of years in this case. So long after that pulsar is dead, that star begins to evolve. It turns into a red giant, begins to transfer material into an accretion disk, which is just where it's dumping material and angular momentum onto that neutron star. So that adds mass, and it causes that neutron star to spin rapidly. That material is also highly ionized, and it buries a large fraction of the magnetic field under the accreted material. So that pulsar loses a lot of its magnetic field as well. Finally, when that star finishes its evolutionary process, its outer parts are ejected. What's left over is the white dwarf core, just like our sun is going to be in about 5 or 6 billion years. The white dwarf core in a perfectly circular orbit around a rapidly spinning millisecond pulsar. And those are the key characteristics of most of the millisecond pulsars that we see. There's a white dwarf companion object in a perfectly circular orbit, and a millisecond pulsar spinning hundreds of times per second with a reduced magnetic field of about 10 to the 8 or 10 to the 9 Gauss. So that's the kind of the characteristic system. So those are the systems that we then measure primarily using large radio telescopes. And when we use large radio telescopes, we have to use the largest telescopes because they're incredibly faint objects. We need the largest amount of collecting area to collect the incredibly tiny amount of energy that we receive from them here at Earth. So I'm going to explain how we time these pulsars now, but the graphics are greatly exaggerated. So I'm showing you a time series here with a pulsation. You see every pulse from the pulsar. In general, that's about 1 million times stronger than any pulsar we would ever see. You can never even see, for millisecond pulsars, individual pulses. We have to integrate up many, many hundreds or thousands or even millions of pulses together to get a detection that looks anything like that. So what we generally do is we measure using some kind of potentially a Fourier transform. We detect the pulsar. We see a very pure tone. We then know how to split a time series into chunks, so we can separate each of these pulses. And we can then increase the signal to noise by folding those pulses on top of one another. And that's what we do. We take our data and wrap our data around at the pulsation's frequency, at the pulsar's frequency, so that the pulses, if time is flowing this direction but helically, so this is one pulse rotation, if we just stack these pulses on top of one another, they all line up. And so this dark gray region would be the stack of pulses that we measure. So we're measuring averaged pulses together. As a matter of fact, this is real data from a pulsar. This is one observation. This is about a half hour of data that I've averaged tens or hundreds of thousands of pulses together. Matter of fact, close to 1 million pulses together over this observation. So what you can see is that because the stacks the pulses line up with one another, we know the pulsation period or the frequency very, very precisely. If we didn't, that line would have a slope. If we were off in the pulsation frequency, the pulse phase would drift one direction or the other. So this is the observation. We make a bunch of measurements of where each of these averaged pulses arrive. We call those times of arrival. And those are our data points that we do our physics experiments with. What happens next is we can come back, say, to the telescope the next day and make another observation. And if we have measured the pulsation frequency correctly, we can start rotating the data, folding the data on top of itself perfectly yet again. And what you'll notice is that if you do things correctly, this line here perfectly matches with this line. There's no slope. that line continues. This is what we call the pulsar timing model. That's our prediction of the way the pulse phase, the phase of the pulsation's arrival time, how that phase evolves with time. And the critical thing about pulsar timing is this very top sentence here, that we unambiguously account for every single rotation of the pulsar over a long period of time. So that means that even though we weren't at the observatory observing here, as long as we made this measurement correctly and this measurement correctly, this line perfectly connects here, so we know exactly how many rotations of the neutron star that we missed in that central region, in the region where we weren't observing. And so what this depends on is that we have to time our observations properly so that the errors in our measurements aren't too large that we lose track of this phase. So what typically happens with pulsars is that we'll make a bunch of observations very closely spaced to start establishing this timing model. And then once we have the model established, we can space our observations further and further apart in time. But the crucial thing is that we unambiguously account for every single rotation of that neutron star. So then, once I have a model, in a few more days I can go back to the telescope, I can make another observation. So here's would be a third observation. And you can see now that this model does not exactly connect with that dark line. That's because we're extending and extrapolating our model. So if the error is only small, which in this case it is, it's only a small error in phase, we can improve our timing model. We can make it better using this new data. And now we have a longer and more accurate and more correct timing model that I can predict for the next observation in the future. So this is the way that we make these measurements. The data points look like this. So these are our times of arrival. We show our plots that we call timing residuals, where we take the measurement and we subtract off the model prediction. So every data point in this diagram, you can see a whole bunch of data points together on this day. So that's a day at the telescope, and we didn't observe with a telescope for the months around it. There's a whole bunch of very densely sampled data here, a bunch of densely sampled data there. And what you can see is that these are all basically in a line. This is a line of zero residual, which means that our timing model predicted our measurements very precisely. And for this particular pulsar, which is one of the very best pulsars, the RMS errors on these measurements are about 200 nanoseconds over the time period of 2 years. So that means that out of the billions of rotations of this pulsar over 2 years, I can tell you when any individual rotation of the pulsar arrived at the telescope to within about 200 nanoseconds. And when you can measure the phase of that pulsar that precisely, it gives you incredible information. And I'll show you an example of that right here. So when we publish a timing model and publish a timing solution, our timing models kind of look like this. And this is from a paper where we measured the mass of a millisecond pulsar and showed that it was the first known 2 solar mass neutron star. All of these, from basically this line right here up, are all of the parameters that are in the timing model. So there's of order 15 or so models or timing model parameters that we have to account for. The first 5 of those have to do with position on the sky. And just by measuring the arrival times of the pulses, we can measure extraordinarily precise positions on the sky, because the Earth is going around the sun, and there's a 500-second light travel time delay between the sun and the Earth. And so as the pulses are coming to the Earth is moving. There's thousands and thousands of pulses that we have to keep track of as the Earth goes around the sun. And so using basic trigonometry and projection and counting pulses, we can exactly identify where that pulsar is on the sky. And then as time goes on, we can even measure how the pulsar moves across the sky, the proper motion. That's these 2 parameters right here. But you can see the position on the sky is known to about 10 or so, or 12 significant figures. These are milli-arcsecond or even micro-arcsecond positions on the sky, purely from timing the pulses. We measure the pulse spin period. You can see there's about 15 significant figures there. That's the error bar, that's 6 in the parentheses, that's the error bar on that last digit. So these are some of the most precisely measured measurements in all of physics that we can make for millisecond pulsar timing. Now, there's no physics whatsoever in that number. That's basically a random number. But it's the fact that we can track that number over time that lets us get the physics out. Here's the spin down rate. The pulsar is losing energy, so there's a very precisely measured of how the measurement of the pulsar's period derivative. And here's all the orbital parameters. Here's the orbital period in days of that white dwarf companion I told you about. It's about 12 significant figures. Here's the size of the orbit, about 10 significant figures. The eccentricity, a whole bunch of other parameters. And when you do this correctly, this is what you get for almost all millisecond pulsars. Extraordinary precision. So the key to getting physics out of these measurements is to ask the right question of the pulsar. So I'm going to give you an example of that. So I told you that all millisecond pulsars basically are in circular orbits with a white dwarf. So what does that really mean? How circular? Well, here is the measured eccentricity of the orbit, 1.3. There's the error bar on that last digit there on the 0, times 10 to the minus 6. So that seems like the number very close to 0, but I'm not used to thinking in eccentricity. I'm not sure how circular that really is. Well, we can figure that out. The eccentricity can also be determined in the ratio of the semi-major to the semi-minor axis on an ellipse, and all objects are orbiting in ellipses. So here's the size of the orbit. This is basically the radius of the orbit. It's about 11.3 light seconds. 3.4 million kilometers, that's 5 times the solar radius, etc. So what is the difference between the semi-major and semi-minor axis given that eccentricity? And the answer, including the error bar, is 2.8 plus or minus 0.2 millimeters. Yet this object is several thousand light years away, and we can make that measurement with that kind of precision. So if you ask the right question to a pulsar, you can get extraordinary answers out. And so that's the real key to getting physics out of pulsar measurements. The first group that really did that was Hulse and Taylor with their Nobel Prize-winning observations of the first binary pulsar known. So this object is a highly relativistic system of 2 neutron stars. It's one neutron star spinning fairly rapidly. It's not a true millisecond pulsar. And another neutron star in an eccentric orbit. And this is a highly eccentric system. Here's the precession of periastron, 4 degrees per year, compared to 42 arc seconds per century of Mercury's orbit. Highly relativistic. They measured this using pulsar timing with extraordinary precision. They measured 3 post-Keplerian observables. We'll hear some about PPN formalism and the so-called post-Keplerian parameters later this afternoon, I believe. But that allowed them to measure the pulsar mass and the companion mass, because each of these observables gives a different line on this diagram. And the fact that there's 3 lines, all converging in a point, let them test general relativity to high precision. This is the famous plot that shows that. It shows the decay of the orbit, which shows that gravitational waves were being emitted from this system. So by using pulsar timing, they were able to exquisitely measure the changes in the orbit of that system. And that's the type of measurements that we now do routinely on hundreds of millisecond pulsars to get other types of physics out. So probably the most exciting experiments that are going on right now with millisecond pulsars are using a large number of millisecond pulsars around the sky to try to directly detect gravitational radiation. With the Hulse and Taylor binary pulsar, that was an indirect measurement because they saw the effects of gravitational radiation leaving the system. They saw the orbit shrink with time. With these measurements, we're going to directly measure the stretching and compressing of space-time in our galaxy, and I'll explain how that works. The crucial aspect of this, though, is that we need large numbers of millisecond pulsars, and they have to have incredible timing precision. And it's a long-term experiment. It takes at least 5 to 10 years. And matter of fact, the 3 big experiments around the world, Nanograv in North America, the Parkes Pulsar Timing Array in Australia, and the European Pulsar Timing Array in Europe, these 3 experiments have been going at this now for over 10 years, about 12 years. And what I'll show you over the next few slides is that we think over the next couple years we're approaching a detection. So how does this work? Well, basically, we're looking for the very long period gravitational waves, years periods, that are jiggling space-time in our galaxy, caused from supermassive black hole binaries in the centers of galaxies. Just like what George Drogowski described yesterday about the supermassive black hole binaries that we know must be out there. Those things are generating gravitational waves with years periods that are flowing through our galaxy. And what that does, those gravitational waves shift the pulsars. They cause the pulsars to effectively move in space-time. they also cause the Earth to move in space-time. And so if you think of the pulsars as being parts of our detector, and the Earth as being the other end of our detector, just like LIGO, that you have the test masses at the end of the interferometer arms. In our case, the Earth, which is where our telescopes live, is one end of the interferometer arm, and our pulsars are the other ends of the interferometer arms. So if then a gravitational wave sweeps past the Earth and causes the Earth to shift, for instance, if it shifts towards you, if you are all pulsars, if the Earth shifts towards you, all of your pulses will be slightly early compared to our timing model, whereas pulsars behind me will be slightly late. Pulsars to this side of me will not be affected at all. So there's this very specific correlated signal of how the timing of all of our pulsars will be affected if a gravitational wave sweeps by the Earth. That's the general gist of the measurement. These three experiments have various different strengths and weaknesses. We're all trying to do the same thing. Some of our pulsars are overlapping from each of the various experiments because we only have one sky, even though we have many telescopes. And in general, though, the difference is the big telescopes that we use. In the US and North America, we have the two biggest radio telescopes on Earth, the Arecibo dish in Puerto Rico, which is 300 meters in diameter, and the Green Bank telescope in West Virginia in the United States, which is 100 meters in diameter. Because these are very sensitive and big telescopes, we don't get as much observing time as the other experiments do. They're using excellent telescopes, but smaller and kind of less oversubscribed, so they get a lot more telescope time. We have the benefits of great sensitivity, but they get more telescope time, so they get the benefits of cadence. And in Australia, they get the benefits of the far southern sky, which we can't see from North America. Each of these telescopes has their own advantages and disadvantages. And amazingly, when you look at the way over the last 10 years our sensitivities are for each of these experiments, they're amazingly similar. We're all within a factor of about 2 or 3 in our gravitational wave sensitivities right now, even though we've been working on this experiment for a dozen years. And our latest limits for gravitational wave sources came out basically last summer from each of these different experiments. So here's an example of what the data from the Nanograv's 9-year release, which is what we released last year, looks like. Each of these columns of colored points here are the data we have from a certain pulsar. These are the names of the pulsars. The different colors represent different radio frequencies that we use, and every dot is a day at the telescope, effectively. So what you can see is that we started observing just after about 2005, so this is 2005 up to 2014. And as you can see is that there was only a handful of pulsars in the beginning. We've continued to add pulsars as time has gone on, so that we were timing about 40 pulsars at the end of 2014. We're currently timing over 50 pulsars, and this is one of the big improvements in our sensitivity for these experiments, is the fact that we've been adding new pulsars continuously. Here's what our timing residuals look like. This is that same pulsar I showed you before, but we're timing it much better now. This pulsar, especially we had an instrument change at this dashed line, so from 2010 on, we're using a state-of-the-art new instrument called Guppy. Our arrival times here, our measurements per day are basically 40 nanoseconds is our average arrival time. So over the course of 10 years, from 2006 up to the current date, our full 10-year limit, I can tell you when any pulse arrives to about 100 nanoseconds. So really extraordinary precision on some of these pulsars. So where do these gravitational waves come from? I mentioned that we think our main source is supermassive black holes that are in galaxies that have merged. And this is, we've heard about this several times this week. We think that basically all galaxies have supermassive black holes in them, and so when those galaxies merge by some process, dynamical friction at the beginning, and later when they get very close by processes we don't fully understand, we believe that those black holes will eventually merge. For our experiments, we're not looking at the mergers like they are in LIGO. We're looking at the times when those supermassive black hole binaries are orbiting on years timescales. And that time period that they're in that regime lasts for tens or hundreds of thousands of years for any individual galaxy. So during that time, all of these systems are pumping out gravitational waves into the universe. And the amount of gravitational waves, even though they're tiny, can be substantial enough that we can measure them. So here's an estimate of the change in arrival time that we would see from a supermassive black hole binary of 1 billion solar masses orbiting at 10 to the minus 7 hertz at a gigaparsec distance. And it's about 10 nanoseconds. And I've already showed you that our individual measurements on our pulsars are tens of nanoseconds. So if we average over thousands and thousands of arrival times, we can get to the 10 nanosecond type of level. That's the way the experiment's going to work. And here's an example. I mean, if we had a great binary, a black hole, supermassive black hole binary that we knew where it was and it was close by and big enough, we could measure it directly. So here's a paper that came out in 2003. There's this radio galaxy here with these 2 jets. And using very long baseline interferometry, this group measured a total mass of the system of a few times 10 to the 10 solar masses, and they thought there was an orbital period of about a year. Now, when you're an astronomer, one of the first things you know is that there's at least one other thing in the sky that has an orbital period of about a year. So you always have to be kind of careful whenever you make a measurement of something that has an orbital period of a year. So that was kind of suspicious. But this would be an extraordinary and interesting system for gravitational waves because it's close enough and massive enough and at the right period that here is what that gravitational wave signal would have looked like in our timing data. Our error bars are too small to see on these data points, and these were data that we had in hand at the time that this was published. In other words, we did not see this. So either general relativity is wrong and there's no gravitational waves, which we already know LIGO has showed us that's not the case, or this measurement is incorrect. So this is not a correct system. The systems that George was talking about yesterday are great examples of those we're looking for, and in fact, here's one that he talked about quite a bit, 1302-102. This was published last year. If this thing were about 10 times closer to us, we would be seeing it in our data right now. So we've just really started looking for these systems in other wave bands. There's a chance that one of these systems is out there and we're going to be seeing it in our data soon. Now, in general though, we don't really think that we're going to see a single system. What we're probably going to see first is a background of gravitational waves, a stochastic background. And that comes from the integrated signal of all of these systems spread throughout the universe added together. And so if you think of each of those individual systems as a pure tone, if you take a whole bunch, thousands and thousands and thousands of different tones and add them together, you get noise, just like in a noisy room. We can measure that noise, the properties of that noise. We can measure its amplitude and its spectrum. And people have predicted what that would look like, and you get a very specific spectral index and a good estimate of what the amplitude range will be for a power law type signal. So in general, this is the signal that we're looking for in our data. We think it's most likely that we will detect a stochastic background first. So how exactly does the detection work itself? Well, I already kind of implied that it was due to a correlated effect. Once again, think about that. If I'm the Earth and I'm moving towards you, all of your signals are early, all of these signals are late, all of these signals don't change. Well, I was not talking general relativistically in that simple approximation. That was assuming that gravitational waves are dipolar in nature, but they're not. They're actually quadrupolar in nature. So because space-time gets stretched and compressed in a quadrupolar way, there is a correlation pattern exactly like that, but it's quadrupolar in nature. And if we measure the correlation of our timing from each of our pulsars that are spread throughout the sky, if we measure the correlation function of the timing residuals, there's a so-called function known as the Hellings and Downs curve that explains that quadrupolar correlation function from gravitational waves. And because the Earth is one side that's common to all of these measurements, that Earth causes this correlation signal in our data. The pulsars themselves are also being jiggled, and because we don't know their distances precisely, those cause a scatter around this green line. But if we can make good enough and enough measurements in general, a large number of measurements, we will be able to measure this curve in our data. And that should be an ironclad proof that we've detected gravitational waves and not something else like an error in the mass of Jupiter, because that would cause a correlated timing signal in all of our pulsars as well. Or if we had a problem with the International Atomic Time Standard, that would cause a correlated signal in our data as well. But those are going to be monopole and dipole errors, not quadrupolar nature errors that you'd get from gravitational waves and general relativity. So where are we right now? Each of the groups have, like I said, have had limits that came out last year. These plots at the bottom are from Nanograv's paper. These plots here are from the Parks paper. In general, these colored lines, colored bands that you see here, are the predictions. That's the power law, slope, and amplitude with a big band that describes the error bars of what the predictions are for the gravitational wave background. And these are our noise curves. And you can see that the noise curves are just starting to approach and to cut into these predicted models. So right now, we are in a regime where we're starting to make astrophysically interesting limits on the gravitational waves from these objects. We have not seen them yet, but we're starting to rule out models from these systems. And there's a bunch of explanations as to why we haven't seen anything yet. The easiest and probably most likely explanation is that at least the highest end of these model curves, for instance, if you look at this curve, we're just barely getting into the top of that curve. The most optimistic end of those model predictions are probably just too optimistic. There's a lot of errors in measuring black hole masses and the number of black holes that are in the universe. It's hard to make those measurements. The latest models from just this past year, which have folded in some of these new detection statistics, and have used some new and better techniques. For instance, there's these new, very fancy cosmological simulations called Illustris, which basically seem to match our known cosmology that we've now measured very precisely over the last couple decades. And in their new models say that they predict that the best estimate of where the gravitational waves are is about 30% below our observational limit. And another paper just came out on the archive this week from Sesana et al. That show that there's some idea that supermassive black hole masses have been slightly biased high in their measurements. If you factor that in, once again, these bars go right below our measurements. These are the three groups where our measurements are, so the predictions are actually just below our levels. But the neat thing is that our measurements improve. We move down this direction quite rapidly in time. And so here's the predictions for the future. So this gray band represents the gravitational wave strain predictions from all these models. The newest models I just described are just below this band. They come out about right in here. This is our 95% upper limit track. Our publication from this past year showed up right here. That's where we are. We're biting into this band. Here's the Parks upper limit from last year. They're also biting in about halfway into this band. This red line shows our 95% upper limit predictions given our current experiment. And we will be below this band within the next 2 years, 2.5 years. This green line and blue line show the 50% and 95% detection probabilities. So if gravitational waves are at this level, this is a 95% detection probability that we will make a 95% detection. So it's a 95% chance that we'll make a detection at 3 sigma, is basically what this line shows here. And so you can see that over the next 5-ish years, I think we have a really, really good chance of getting a detection, even using the very, very best models on supermassive black holes in the universe. So we want to improve this, though. We don't want to keep just doing what we're doing. We want to do better. One way to do that is we can take all 3 experiments and combine them together, and we're starting to work on this. It's called the International Pulsar Timing Array, and if we combine all of our data, we instantaneously get a factor of about 2 improvement in sensitivity. The problem is each of these groups has a bunch of egos, each of these groups has a bunch of their own systematics and problems, and so it's tough to get these 3 groups working together. I'm actually chairing the group that's combining the data for a current limit paper, and it's a total nightmare working with 3 different groups who each have their own agendas. But that's science and sociology. But anyway, we think this is going to help out a lot, but each of the individual groups are going to continue to work as well. But how else can we do better? Well, there are 3 main things that we can improve: instrumentation, we can find new millisecond pulsars, and we can use bigger telescopes. And each of these things actually will help with all of pulsar science. And just to show you how much instrumentation and telescopes have actually, and computing have helped, this shows kind of a Moore's law improvement. This is basically a logarithmic scale of how good our timing has been as a function of time. The first pulsars were in the early 70s. compared to now, we're in this regime down here, sub-100 nanoseconds. Our timing has improved by orders of magnitude since the first pulsars were known because of the improvements in instrumentation, bigger telescopes, and finding new pulsars. So here's an example of how some new instrumentation will help us. 10 years ago, we were observing a very small amount of radio bandwidth. This is a radio frequency where pulsars normally observe. This was a state-of-the-art instrumentation 10 years ago. This is what Nanograv was using for our first 5 years of observation. Then we upgraded to Guppy and Puppy, and we have an order of magnitude more radio data that we are measuring at once. That gives us dramatically improved sensitivity, and it lets us nail down some other systematics due to the ionized interstellar medium, for instance. What we want to build right now is an instrument that'll take all of this data all at once. These are very hard to make. These are very, very tough receivers to make, especially at this broad of a bandwidth. And we have some research projects and some initial development work that's ongoing right now. But that would improve our measurements by a factor of 2. The next big thing is to find new pulsars. And every big radio telescope on Earth is undergoing pulsar surveys right now. And that's because even though the sky has been surveyed many times in the past, because they didn't have the computing capability or the sensitivity of their radio receivers, they missed huge numbers of pulsars, and especially the millisecond pulsars. So every big telescope is undergoing massive surveys. We're taking many petabytes of data. And this is important because the sensitivity to gravitational waves is directly proportional to the number of pulsars that we're timing. This was something that was just realized a couple years ago. So all we don't need the absolute best pulsars, we just need good pulsars and lots of them. And the way to think about that is that on that correlation curve I showed you, every data point on there comes from a pair of pulsars. And the number of points from correlated pairs goes as the square of the number of pulsars. So this is why we want a large number of pulsars. Here shows you how the number of millisecond pulsars has changed with time. And you can see it's grown dramatically just in the last few years. We've more than quadrupled the number known in the last 10 years and doubled the number known in the last 4 years. And we've been adding these to our timing programs. The Fermi Gamma Ray Space Telescope has been fantastic. It's seen gamma ray sources that were not explained by active galactic nuclei. And Fermi has shown that all millisecond pulsars give off gamma rays. So if we see a point source in the Fermi sky that doesn't have an active galactic nuclei, we've pointed our radio telescopes at that source and found some nice new millisecond pulsars. So this is a great way of getting multi-wavelength astronomy helping each other out. And we found 70 new millisecond pulsars from doing this type of search technique. Many of the new millisecond pulsars we're finding are very interesting for other reasons as well. Here's a new system that was found at the Green Bank Telescope a few years ago. It's the second neutron star system that's 2 solar masses to high precision. And this is incredibly constraining for nuclear physics and the interiors of neutron stars. There's 2 of these systems now, and the nuclear physics community at high density has dramatically changed by these 2 measurements. Other systems, so-called black widow systems, these are binaries, millisecond pulsar binaries where there's a tens of Jupiter mass companion, so very, very small companion star. The radio emission is eclipsing, these behave very strangely, but those small companion stars can be seen in the optical and the infrared. And if you measure the pulsar timing and combine it with optical and infrared measurements, it looks like some of these systems have even more massive neutron stars, more than 2.1 solar masses, for instance. The problem is modeling these optical light curves and optical spectroscopy is very, very difficult and prone to a lot of systematics. But a lot of people are working on that. Here's another example of a very strange system we found a few years ago. I told you that all millisecond pulsars have perfectly circular orbits. We found one, and white dwarf companions. We found this millisecond pulsar in a highly eccentric orbit with a main sequence G-star companion, just like our sun. Turns out this is a beautiful object. We time it for Nanograv. We've measured its mass. And it looks like, when people try to explain how this system came to be, it was probably at one time in a triple system. And so there was 3 stars, and the star that made it a millisecond pulsar, the star that recycled it and became a white dwarf, almost certainly was ejected from the system in a dynamical encounter probably billions of years ago. So this implied that triple systems with millisecond pulsars should exist in the galaxy. And sure enough, a couple years later, we found one in one of our pulsar surveys. So we found this very interesting system. So this is a hierarchical triple system with a millisecond pulsar in 2 white dwarfs. So it's 3 compact objects. There's an inner orbit that's this cyan circle here, and that's, if you blow that up, there's the pulsar in the center, and a young hot white dwarf here orbiting every 1.6 days. And then that little orbit there is orbiting about the center of mass, because there's a white dwarf out here that's orbiting every 327 days. This pulsar is a beautiful pulsar. We can time it to 100 nanosecond precision, and the timing is extraordinary. So let me show you what some of the data look like. So this is the time delay. Because the pulsar is being delayed as it moves around the system, as it goes further away from you, we see the time being delayed. As it moves closer to you, we see the time being advanced. We're just measuring light travel time differences, which is exactly what this is. So that outer orbit with 327 days causes this. These are our data points here. And it's astonishing because our error bars there are 1,000,000 times too small to see. Our measurements are at the sub-microsecond level, and these are delays of seconds. So if you zoom in on this little region right here, you can see that's this bottom panel, and there's the 1.6 day orbit. Once again, since this is still measured in seconds, our error bars are still 1,000,000 times too small to see, even on this bottom plot. So we have extraordinary measurements of this system, including 3 body gravitational effects that have completely allowed us to totally solve the system. All the angles, all the masses, exquisite precision. Here's the masses of the neutron star, the white dwarfs, 5 significant figures on each of them by high performance timing combined with a 3-body dynamics model, including special relativity. We have to include time dilation in order to get this all to fit, and it fits beautifully. But one of the nice things about this is going to be a great nanograv pulsar for gravitational waves, but we also get an excellent side benefit that it's going to be a fantastic test of the strong equivalence principle. So what exactly is that? So the weak equivalence principle is what we know of. It's primarily the equivalence of inertial mass and gravitational mass. It's also the universality of free fall. And here's just a clip that shows a feather and a bowling ball being dropped in a massive vacuum chamber in one of Brian Cox's shows. And you can see they're falling at exactly the same rate there. That's basically the weak equivalence principle. The strong equivalence principle adds something different. And the strong equivalence principle says that strongly gravitating objects also gravitate. In other words, the gravitational binding energy also gravitates. And interestingly, general relativity is the only workable theory of gravity that we know of right now that the strong equivalence principle holds for. Basically, all other theories of gravity that are workable, that at least we know the dynamics of cosmology and stellar objects that they follow. This is the only theory of gravity that's workable where this applies. And so what you can think about for this is that the ratio of gravitational to inertial mass is basically 1, plus there's a tiny perturbation here that we can use to test. And that perturbation has a thing called the Nordtvedt parameter, as well as this term called epsilon. And the epsilon here is basically the gravitational binding energy. It's gm over rc squared. For a black hole, that's 1. For a neutron star, it's about 1/10. But for white dwarfs and planets and suns and stuff like that, it's a tiny number. A white dwarf is about 10 to the minus 6. For a planet or the sun, it's about 10 to the minus 8 or 10 to the minus 9. And in this system, this is very interesting because what we have is we have a highly gravitating object, the neutron star, and a lightly gravitating object, the white dwarf, and they're both falling in the gravitational potential of that outer object. So it's exactly like the feather and the bowling ball falling in the Earth's gravitational field, except this time our bowling ball has a very strong gravitational field. The best limits on the strong equivalence principle right now come from lunar laser ranging. The problem with their measurements are that this epsilon term is the sun and the planets. It's 10 to the minus 8 or 10 to the minus 9. In our case, it's a 1/10. And using just our initial data, just the fact that our data fits, you can qualitatively say that we're substantially better than lunar laser ranging. If you do some numerical experiments, this shows you the signal that we would see in our data. These colors, you can just think of them as being signals that we would see in our timing data at a highly significant level if the strong equivalence principle were violated at a level that's 100 times smaller than lunar laser ranging. So we're working on a paper right now that should have a limit at least about 100 times better than lunar laser ranging. But this is a completely new and unexpected type of test of general relativity just by finding new millisecond pulsars that are also going to benefit gravitational wave detection. And just because we have a lot of gravity people here in the audience, I want to show this plot. This shows you the limits on scalar tensor theories. These are the alpha and beta parameters, where GR is at 0 on each of those. All of the other astrophysical limits on the scalar tensor theories are shown by these lines. So you want to be down in this, the further down you get, the more constraining. The triple system, this is a plot by Norbert Vex, the triple system is way better than any of these other astrophysical constraints at ruling out parameter space for scalar tensor theories. So in my last couple minutes, I want to just say what kind of the future is for pulsar science in general, and I think it's excellent. The pulsars we know about right now, because they're such faint objects, we are sensitivity limited, and we only know of the pulsars in our little neighborhood in the galaxy. We only know of a few percent of the pulsars in our whole galaxy. We think there's 50 or 60,000 pulsars in the galaxy. We now currently know of about 2,500. Many of those new systems that we detect will be highly interesting for a wide variety of physics. We think that there could be sub-millisecond pulsars, which would constrain the equation of state of dense nuclear matter. Pulsar black hole systems would give strong field tests of general relativity at exquisite precision. Millisecond pulsar binaries would allow amazing astrophysical tests as well as very interesting tests of general relativity using 2 clocks. And to do this, to find these new pulsars throughout the galaxy, we really need bigger and new telescopes, though, because we're kind of pushing the limit of what we can do with our current telescopes. There's 2 telescopes that are coming online over the next year. The Meerkat array of 64 dishes in South Africa, and the 500-meter FAST telescope in China has just finished its construction. Here's a picture of FAST from, I believe it was May. They just finished putting the surface in. This is 500 meters in diameter. This looks very much like the Arecibo telescope in Puerto Rico. You may have seen pictures of that before, but Arecibo is 300 meters, not 500 meters. And if you zoom into this center region here, this little pentagram right here, that's this region right here. And what I want you to notice is that these things right there, those are people. This is huge. This is a huge, huge collecting area. This is going to be a fantastic telescope for pulsar experiments in general. And then the big goal for us for the pulsar field is the square kilometer array, which hopefully will come online in the next decade. It's a very expensive project, though, international. Sometime after 2020, 650 million euros for the phase 1, but the real one that we really would like to see is phase 2, which is a full square kilometer of collecting area. That would let us see every pulsar in the galaxy. That costs a lot more, though. That's the problem. And it would be 2 instruments, low frequency array in Australia and high frequency array using dishes like Meerkat scattered throughout South Africa. And this would be spectacularly interesting telescope for pulsar science. So in summary, I hope I've shown you that I think there's a lot of very interesting physics that we can do with pulsars. Direct detection of gravitational wave, I think, will come from supermassive black holes, a new window in the gravitational wave spectrum. Just like radio waves and X-rays are different and show us different science in the electromagnetic spectrum, these nanohertz frequency gravitational waves will show us different things than the hundreds of hertz or kilohertz gravitational waves we get from LIGO, as well as a whole bunch of other basic physics as well. Tests of gravitational theories, tests of the nature of matter at supernuclear density, and a whole bunch of astrophysics as well. The problem right now is we're sensitivity limited. We need to keep our current telescopes. The GBT and Arecibo are both under threat. And if we lose those, the pulsar community is going to be heavily hurting, and nanograv will have real trouble making a detection in the next couple of years. But over the decades, the next decade after that, internationally at least, I think the pulsar community, it's very exciting because of these new, very sensitive telescopes that are coming online, especially the SKA. And I'll stop there. Thanks.
Thank you very much. Questions or comments? Yes.
One question concerning the sensitivity. Do you really need this huge telescope, or would not a large number of moderate-sized telescopes distributed over the Earth do the same job? Maybe you could even build dedicated telescopes just for this purpose.
Yeah, exactly. So the crucial aspect is collecting area. You just need, whether you do it by a whole bunch of small dishes, when that's the way the square kilometer array is going to do it, all these thousands of small dishes added together, or single big dishes, what we need is collecting area to find these incredibly weak signals. Now, there is one problem though. I mentioned, I didn't really talk about it, but when you spread your signal out with a lot of largely spaced telescopes, what you get is resolution. This is how very long baseline interferometry works. You get small pixels on the sky. That is terrible for pulsar astronomy, for searching for pulsars. We don't want tiny pixels because every pixel has to have a huge amount of data just for it to find the pulsar. So array telescopes like this are great to time the pulsars that we know about, but are really difficult to let us find new ones. So, matter of fact, the SKA, one of the big costs of the SKA is designing a very special high-performance computer system that will allow us to find pulsars, because pulsars are one of its main key science objectives. But that's a huge, huge cost to get rid of that resolution. The resolution that almost everyone wants, we don't want that resolution.
Well, my question was not related to looking for new pulsars, but to get a better timing for the existing pulsars. You see, if you treat the distance from the Earth to the pulsar as a large, so to say, large interferometer arm, then I think the timing is essential. In the moment you have to average over many periods. If you can reduce the time for averaging, in the extreme case maybe even resolve an individual peak, then I think this would have a much better resolution for the detection of these gravitational waves. Or is this not
That's
true?
actually not true. It's not true. And here's a simple explanation why. So the gravitational waves are nanohertz, so they're years in time period. So if we were to measure individual pulses, those are at the millisecond time periods. That's how many orders of magnitude? 9 orders of magnitude different than the time period that we're looking for. So since we're looking for effectively sinusoids, we're looking for slow variations at very long time scales, having the very, very fastest sampling doesn't help us. What we need is to get rid of the systematics on our individual measurements so that we can average together many measurements to see that very slow but low amplitude drift. So that's the actual really crucial part. And very interestingly, we're working very hard on figuring out what our noise is in our timing observations, characterizing all the different parts of noise. And there's a crucial part of noise that comes from pulsars that if you average fewer and fewer pulses, so if you get down to measuring every individual pulse, you have a huge amount of extra error because of the fact that the pulsar emission mechanism, it's a noise mechanism itself. It's a noise process, so every individual pulse looks completely different from every other pulse. It's only when you average together thousands and thousands of them that you get a nice pulse that you can measure precisely. So in order to make the best measurements, we have to sum and average together thousands and thousands of pulses. Otherwise, this so-called jitter noise, this self-noise caused from the pulsars themselves, kills us.
Okay, thanks.
Yes, Roberto.
What's the distribution of the pulsars in galactic coordinates? And if most of them are close to the galactic plane, then you would mostly be sensitive just to supermassive black holes with a line of sight on the plane of the Milky Way. So what's the situation with that?
Yeah, so this is right. So because we're sensitivity limited, and I mentioned that almost all the pulsars are very close to us in our galaxy, we can't see any kind of galactic distribution in our millisecond pulsars right now. They're all so close that we see them isotropically. Millisecond pulsars are very old, so they've had time to drift and diffuse out of the galaxy, so we see them isotropically. But when we go to the SKA in the future, if we find all of the pulsars in the galaxy, there will be a very strong concentration of millisecond pulsars, the distant ones that are along the galactic plane, and especially in a very large region around the galactic bulge. But there will still be thousands of them that are still isotropically distributed near us. And so as long as we have a semi-isotropic distribution so that we can probe all those different length scales of separations on that Hellings and Downs curve, that lets us measure all those spatial scales for correlations, then we're good. And so I think even with the SKA, we're going to be completely fine with the distribution of pulsars.
Yeah, can you do this part of this work with the slower pulsars? I mean, millisecond pulsars, yes, they are best because they are so fast. They give you more pulses, or they have something else.
Yeah, so they also have something else. So you can think of the timing precision that you can get is related to the time duration length of a pulse. And all pulsars, the best pulsars, have a width of a few percent of a pulse period. So if you have a slow pulsar that's a 1 second pulsar, its width is a few milliseconds of that pulse. But if you take and make that pulsar spin 1,000 times faster, its width is 1,000 times smaller, and we can measure the precision about 1,000 times better. So that's one thing. The pulsations themselves are much narrower. That really helps us. The other thing that's very important is that because their magnetic fields during the accretion process have dramatically decreased by 4 orders of magnitude, and these are very old systems, these systems behave beautifully. You may have heard of pulsar glitches. These things don't glitch. There's very little or no timing noise. Young pulsars show, because they're hot, they have strong magnetic fields, their magnetospheres are doing things. They are not nearly as stable clocks as millisecond pulsars are. So those two things make millisecond pulsars way better than slow pulsars.
Okay, so they are really great tools. More questions or comments? You were also involved in all this fantastic detection of pulsars that were more massive than the people believed. So can you sort of summarize what's the status of the field after your detections, and what's the explanation and that?
Yeah, so like I said in the talk, nuclear physics has really, especially those who study dense nuclear material, has been basically revolutionized by the detection of 2 high-precision measurements of 2 solar mass neutron stars. And the reason for that is that when you get much above nuclear density, and that's what, for these massive stars, you're a couple times at least nuclear density in the center, the nuclear physics gets highly nonlinear as you continue to add mass. The central pressures and densities go up very strongly, and what happens with nuclear physics, whether you get new particles such as hyperons or kaons or things like that, or whether you continue to have pure nucleons, whether 3-body interactions become important, all of these things are currently unknown. But by measuring higher and higher mass neutron stars, it strongly constrains the physics that's going on the interior. So there's a huge amount of work that's going on to those right now. And the pulsar people are trying desperately to find even more massive systems, because even a small increment, because of how nonlinear it is, yet again strongly constrains the equations of state.
Questions or comments? If not, well, let's thank Scott again.
Thank you.
And we will have our coffee break now and be back at 11:30. Thank you.